Hello everyone, welcome to the fourth lecture of this series on foundation design, analysis and design on SAFE. So in our previous sessions, we have seen how to check the pressure, how to size the footing, and we have also seen how to decide the thickness based on the, you can say, two-way shear, or you can say the punching shear. So the punching shear that we have seen, it is the automatic calculation that SAFE does, but how it is being done, that also we need to see here, okay? Or if we can do that manually in SAFE, that also I will show you. So one thing I just want to correct, I think by mistake I explained that wrong, that suppose you have the footing, I'm taking our you can say condition only, this is the footing, and here we have considered the final, like the depth now we have considered is 800 mm. Okay, and for this which are getting some punching shear of 0.7 something, right? And here if you see, we are getting the pressure, so now what I have explained earlier, that this depth, the total depth, we have 1.5 meter we considered, okay, and we have 800 mm you can say footing depth. So now here we will be having soil, so this soil load will be applying here to get the gross SBC, okay, or gross pressure, not gross SBC, we will be getting the gross pressure. Now what will be the limit? Now this gross pressure, obviously it will be, suppose 1.5 minus 0.8 meter, and if we want to apply the load, so it will be 1.5 minus 0.8 meter multiplied by 18 kilonewton per meter cube, which is the density of you can say soil, unit weight of soil, and you will get some load. Okay, so it will be around 12.6 kilonewton per meter square, which we have applied as 13 kilonewton per meter square here. Fine. So this is the load you have applied, due to which you will be getting the gross pressure in terms of your reaction. Now what will be the limit? So basically the limit is not, when we will be calculating the limit, what will be the, you can say, acceptable limit? In that case, we are considering that this is my depth, and at this level, what should be the gross pressure? At this level, at which level? At 1.5 meter level. Okay, so at this level, what should be the gross pressure? So when you will be calculating, you can say the gross SBC, the gross allowable SBC, in that case it will be 300. Suppose we consider 300 kilonewton per meter square, right, as our net SBC. The gross SBC will be 300 plus this total depth 1.5 meter multiplied by the unit weight of soil, and then we will be getting a value which is the limit. Okay, so that earlier what I have explained, I think I have explained like this: the 300 plus sorry, I think yes, 300 plus, here what I have explained, let me just calculate this, how much will be getting 300 plus 1.5 multiplied by 18. So this 327 kilonewton per meter square, it will be our gross SBC, and this will be our limit. I think earlier what I have explained, like this, that 300 plus 1.5 minus 0.8 multiplied by 18, this will be our gross SBC. No, the allowable gross SBC, when we are taking at this particular depth, at a depth of 1.5 meter, right? But when we are applying the load, for this we will be applying the load for this particular depth only, because here only we are having the soil, and rest we have the our footing. Okay, so we will apply this load on the surface of the footing, then we will be getting the gross pressure, and with that gross pressure we will be checking with this gross SBC. Okay, so the gross SBC is, for us it is 327. I think am I doing wrong? Right, 3000 300. Yes, okay, right. So I hope it is clear now. One thing is gross pressure. That gross pressure will be calculated applying the load taking this particular depth of soil, and the gross SBC will be calculated applying the load considering this particular depth, which is the whole against the founding level, depth at founding level. So in this case it is 1.5. okay, not this. Okay, so now 327. I think our footing is clear under this pressure. So if you just see, let me just run the analysis, and if I go to here, I'll take this service load combination and I'll click on apply. So here you can see it is clear under this pressure. So we are getting a gross pressure. You can see this Q load, which is this Q load is nothing but the soil load that we have applied, the overburden load we have applied. So considering adding this Q load, whatever pressure we are getting, this is my gross pressure. So this is the reaction that we are getting. This is the gross pressure. So how much gross pressure we are getting? Suppose 286.38 kilonewton per meter square. And what is our limit? So our limit, our gross SBC allowable was 327 kilonewton per meter square. So our gross pressure 286 kilonewton per meter square is less than our gross allowable SBC. Hence, okay. So if I made any mistake in our earlier sessions, please do correct it in this way. Okay, the allowable will be considered taking the whole depth of the founding level, and when we are going to apply the load on the you can say footing, the soil load, obviously whatever soil depth we have, we will be applying for this only. Okay, and then the pressure we are getting is the gross pressure as we are adding the soil load on it, and the SBC after adding the whole depth, the soil load for the whole depth of the foundation, means for the founding level up to the founding level, that will be considered as my allowable gross SBC. Fine. Okay, fine. So now I will just close this. Sorry. Okay. So now what I will do, as you already seen that in the load combination we have added that 1.5 dead load plus 1.5 live load, and when I press show punching shear, let me run the design again. Run analysis and design. Okay, so I think it is ready. Now if I go to display, show punching shear, you can see the punching shear is showing 0.722. We can reduce the depth more, maybe we can make it 750 also, but I will stick with 800 for now. Now this is one criteria for finding out the depth. Now what will be the another criteria for finding out the depth? The another criteria will be my you can say one-way shear. Another criteria will be my one-way shear. Okay, so that means suppose this is my footing. Here we have the column. So for this column, as the load is coming like this, we consider that the punching shear will be at a vicinity of d/2 distance, right? And one more shear we consider is my you can say one-way shear at d distance. All of us know. So at d distance, like a beam, suppose we have a beam, and what is the shear vicinity? So we consider that d distance. It is the critical section for shear. So here this d distance, it is the critical section for shear here. This at d/2 distance, we are considering as we are having a load like this, like a punch on the footing. So that first we will check for the punching shear. If it is okay, then we will be checking for the one-way shear. Okay, and most of the cases you will see that the one-way shear will be a governing case. Okay, so the vicinity for the one-way shear is at d distance. So at somewhere here. From face of the column, it will be at d distance. And two-way shear, it will be like this, as it is a punch. So if the shear happening, suppose the two-way shear happening, shear failure happening, so you will see the column is going out like this, taking a bunch of your concrete, it will be going out. So this kind of failure, it is the punching, like a piece of paper. If you just punch on it, so it will shear down, shear, right? Suppose you have a piece of paper, and if you are punching on it, so what will happen? It will shear from here. So the same thing is here. Okay. And one-way shear, now we need to check. So now what I will do, I will just unlock the model. I will create the design strips here. Okay. So to create the design strips, I will just click on this draw design strip. Here you can see we have type of object is strip. Now layer, this layer is you can choose any layer. So suppose this direction we are considering layer 1 or layer A, and this direction we are considering suppose layer B. Now you can interchange also, or we can keep both in the same layer, but for our visualization purpose we keep different layers for the different directions. So now as the column, see this column strip and middle strip, it will not change any of your results, but for just for your understanding, or just for your for a better you can say representation of the results, that's why there is a different you can say strips given. That means the strips which are inside in the vicinity of the column, those will be column strips, and the strips which are away from the column, it will be middle strips. Okay, so now here what I will do, as our footing is a small isolated footing, I will draw only a column strip. That means we know that at the face of the foundation column, we are having a maximum moment, right? We are having maximum moment. Like if you see, this is my footing, this is my column, here I have the soil, so the load is coming on this. Okay, it will be going like this, right? So it will be kind of a cantilever effect from here. So at this section we will be having higher bending moment, right? So that's why what we will do, we will draw a strip like this, and we will find out whatever forces we are getting in this strip, and for that forces we will be providing the reinforcement. What you can do, you can also draw a middle strip also. Suppose middle strip covering this area and another middle strip covering this area, that also you can do. But for this small footing of 3 meter by 3 meter, we may not be doing this. We just take one strip at the middle. Now this strip also we can add this total 3 meter I can say footing in one strip, like this side 1.5 meter, that side 1.5 meter. The strip will cover the whole footing. That also you can do, but that will be more conservative approach, because in this sections the I can say forces will be moments will be very less, right? And that's why we will be taking a strip like this. Now what will be the dimension of the strip? So as it is a column strip, and we want the shear also to be calculated. Okay, so shear at a distance of D, right? So now what we will do, we will, in general practice there are different practices actually. You can make these strips of 1 meter, then you can for per meter you can say forces, to get the forces for per meter width. So if you draw a strip of 1 meter width, if it is 1 meter, then whatever forces you will be getting, it is for per meter width. Okay, now suppose you have drawn a strip of 2 meter. In that case, whatever forces you are getting, if you divide this by 2 meter, then only you will be getting forces per meter width, right? So now if you draw 1 meter, then again you have to draw another one. So what I will do in general practice, it is done that this column width we have to left, right? So column width plus, in this direction we consider D, in this direction we consider D, so plus 2D. Though it is not written anywhere, in general practice it is also done that B plus 1.5D also considered. Not B, like column width. Let me write column. Let me write it properly. Sorry. Okay, so column width plus 1.5D. This is also considered in some of the by some of the engineers. So what you can do, you can, if you have very confusion about this, you can take directly 1 meter. So this width will be 1 meter. So in left side, suppose now we are drawing horizontally. So remember always, if you are drawing the line horizontally, the start will be your left side, the end will be your right side. If you are drawing the line vertically, the bottom will be your start, the top will be your end. So when you are starting from left to right, this is your right, this is your, sorry, this is your left and this is your right. When you are starting from bottom to top, then this is your left, this is your right. Okay, suppose you are standing like this, so this is your left, this is your right. Okay, right? So in this way you have to remember, because here if you see, start with left, start with right, that means at this start, at the left, what will be the width? So if it is 1 meter, so it will be 0.5 meter, like this. Okay, now let us jump into our method. Our method is what we do, column width plus 2D. Okay, so if we do column width plus 2D, our column width, I think what we have considered, draw, let me see, draw dimension lines. I will draw the dimension line. It is 0.45, it is 0.45. Okay, and our depth of footing, total depth of footing is 800 mm. Fine, total depth of footing is 800 mm. Now if it is 800 mm, so what will be the D? Suppose we are considering clear cover as 50 mm, and maybe we will be providing 16 mm diameter. Suppose we are considering 16 mm diameter. So 50 plus 16 mm diameter we are considering. Okay, so how much we are getting? So 800 minus 15 plus 60. 50 plus 16. So how much we will be getting? So 800 minus 50 minus 16. Sorry, not 16, 16 by 2. Half of this. Now we need the effective depth. So 16 divided by 2. So how much are we getting? We are getting 742. Okay, so suppose we are considering 740 mm as our effective depth. Fine. So column width is 450. So 450 plus 740. So how much we are getting? 1190 as our total width of the strip. Okay, total width of the strip. So rather making it 1190, maybe 10 mm we will increase and we will make it as 1200. We'll make it as 1200. This is our strip width. So let us draw the strips. How will we be drawing? So let us click on this. Now our strip will be column strip. The layer we are making A as we are drawing from this direction. Okay, and this start with how much? So 1200. That means at one end it will be 600 in one side. So 0.6. Start with right, it will be 0.6. So total 1.2. 1200 we are getting 0.6. So it is in meter. Okay. Same for the right also. 0.6 and 0.6. Fine. Now we'll be drawing, as we have it is a concentric footing, so the column is at the center itself. We can easily draw it like this. I will change the strip as B for this direction, and again we will be drawing like this from bottom to top. Okay, so we have drawn the strips here. Now if you want to see the strips, width of the strips, then you can just right click, sorry, click on this set display options. You can click this show width for design strip layer A, layer B. Suppose I want to see only layer A, so you can see the width for layer A. Okay, so this width we know 1200, and if you want to see only layer B, you can uncheck this, you can check the layer B. And if you want to see both, you click on both and click on OK. Make this show width, click on OK. So you can see this strips of 1200 total width we have defined. Fine. Now what you have to do, after assigning the strips, you just run the analysis and design, and make sure your design combination is selected as the design combination you wanted to use. Okay, click on OK and run the analysis and design. Okay, so analysis and design is completed. Now what I will do here, I will go to this show strip forces. Okay, I'll change the load combination to my design combination 1.5 dead load plus 1.5 live load. Now the first thing is our shear force at D distance. So I'll click on this shear force. Okay, and suppose I want to see for this direction, I'll click on apply, and here it is showing the shear force. Okay, so now if you see, let me turn on the show values of diagram also. So it is showing at this particular end, but we want here, we want somewhere at D distance. So if you see from here, where will be the D distance? So if you see the, just let me turn off this one for once. This point, this face point, it is, if you see this axis here, just have a look on this particular axis. So the on this face, the coordinate for x is 0.225, 0.225, and so this x equal to 0.225. now at D distance, our D is 740 mm, so 0.225 plus 0.740, how much it will be? 965, 0.965. so at D distance. Okay, so the coordinate value of 0.965, you can see 0.975, 0.95. Okay, so you can say that 0.97 is somewhere here, 0.97. Okay, so you just have make a mark on this area. Okay, so this is my D distance equal to 740 mm. Fine. In the same way, we'll be doing in this direction also. If you see, it is minus 0.225, so minus 9.7 or 9.65, 0.965. So minus, you can see here, minus 0.97 in this location. So here I will be having D equal to 740. So in this location, that means this face I am talking about, this total face, as the strip width is this, so this face I am talking about. Okay, so if you draw a cross section in this face, it will be something like this. If I draw a cross section, it will be something like this. So this width is 1200. Okay, this thickness is 800, and this is the face where we are checking the shear force. Okay, so what is the shear force value that we are getting? So if I click on apply, so at this particular location, let me just click on okay. If you go here, you can see it is 450.365. in this direction, here it is 450.365. so I will write, sorry, VU we are getting 450.365 365 kilonewton. Now for this is for how much width? So it is for 1200 mm width, but we want this to be for 1 meter width. What is the per meter shear for per meter width? So what we have to do, so this 450.36 465 kilonewton need to be divided by 1.2 meter, so that then only will be getting the force in kilonewton per meter. Okay, for per meter width, though shear force we get in kilonewton only, but here as it is a slab, so we need to find out for per meter width. So 450.365 divided by 1.2, that we are getting 375. So that means at d distance, so somewhere here you can see 97 it is. So basically we are getting a shear force of 375.304 kilonewton per meter width. Okay, so this is my shear force. Fine, this is my shear force. Now I have to check what is the shear capacity of my section. Okay, I need to check what is the shear capacity of my section. So how to find the shear capacity of the section? So the shear capacity of the section we can find using this table 19 of IS 4562,000. You can see the design shear strength of concrete 𝗃𝐶, and it depends on the AST provided. Okay, so if I tell you that what is the minimum AST that we'll be providing here. In a previous session, I think I have not covered this. So what is the minimum AST that we'll be providing? So let us just consider this as a beam. This as a beam. So this beam is of 1200 by 800. And what is the for tension? For tension, what is the minimum reinforcement required? What is the minimum reinforcement required for beam? So it was PT equal to 0.85 by Fy, percentage of reinforcement, right? 0.85 by Fy. So what will be the minimum percentage of reinforcement in any beam? So it will be, basically the formula was minimum area of reinforcement. Sorry, let me just change the mode. I think I'm in stat mode. Let me change it. Okay, so here what I was saying, okay, minimum AST, so the formula was 0.85 by Fy. Suppose for our case the Fy will be 500 grade multiplied by B into D, so that will give you the area. So this is the percentage multiplied by effective area, that will give you the minimum reinforcement area required. But we do not need area, we need only the percentage. So we can directly get 0.85 by 500. So in that case it will be 0.17%, right? 1 2 3, yeah, 0.17% is the minimum percentage of reinforcement we need to provide in any beam, okay, for tension. Fine. So here if you see in this code, it starts from 0.15. obviously we will be going with 0.17. okay, we don't know how much reinforcement we are providing. Obviously if you increase the reinforcement, the shear capacity will be increasing based on that. The one-way shear capacity or the design shear stress will be increasing. Now here not design shear stress, design shear strength will be increasing. So now what we can do, initially when finding out the thickness, we can go with the minimum reinforcement, which is, even if you are not required any reinforcement, we will be providing that for sure. Okay, so the minimum reinforcement, then only we can find out the depth easily. So what will the minimum reinforcement percentage? 0.17. So for 0.15 you can do the calculation. You can do the calculation. So we'll be doing the linear interpolation here, right? So I'll go to my stat. Okay, 2. Yeah, we'll do the linear interpolation for 0.15% or less, and our grade of concrete is 125. The design shear strength is 0.29 Newton per mm square. So I will write it here. For 0.15, the design shear strength is 0.29. Okay. For 0.25, it is how much? It is 0.36. Okay, so 0.36. Right, now we need for 0.17, so something in between 0.17. Right, so I'll click on AC, I'll press shift stat, I need this one and 5. Yeah, so sorry, I think I have done mistake. Let me do it again. Stat 2, sorry, mode stat 2. Yeah, so 0.15, it is 0.29, right? Or 0.25, it is 0.36. Okay, so now I'll press AC. Now what is our value? Our value is 0.17. Okay, for 0.17, what will be the value? Okay, so I'll press shift stat 5. Yes, I'll click on equal to, so it is 0.304. so the value in between is 0.304 Newton per mm square. Okay, 0.304 Newton per mm square. Fine. So the value that we have got, is 375. So here what we have found out, the design shear strength. Okay, so this tau c, now we need to find out the shear capacity. So how will we find out the shear capacity? So the VC equal to tau c multiplied by B into D. Okay, so tau c, it is how much? Tau c it is 0.304 multiplied by, or B is how much? So we are taking for 1 meter width, right? So 1 meter. Okay, I think I have said it something wrong. Okay, yeah, 1 meter per meter width we are finding out, right? So 1 meter multiplied by depth, so it is 740 effective depth. So how much we are getting? The shear capacity. So it is, we can do it easily. So how much we are getting? We are getting 0.304 multiplied by 1000 multiplied by 740. So it is around 224960. So 224960. Okay, it is Newton per meter. Sorry, Newton per mm. Okay, now if we convert it to kilonewton per meter, how much it will be? It will be 224 kilonewton per meter. But our shear that we are getting, it is 375 kilonewton per meters. So for this minimum reinforcement that we are providing, for this thickness that we have decided, it is not okay, right? I think I have not done any mistake here. 0.17%, we are getting the design shear stress as shear strength as 0.304, right? The other way you can do that, we have got the shear force as 375 kilonewton per meter. Okay, so this 375, if we divide it by our area 1000 multiplied by 740, then how much we will be getting? 375 divided by 1000 divided by multiplied by 740. So we are getting 1, 2, 3, 4. So 0.506 Newton per mm square. Okay, so you can see this is greater than this value, then also it is not okay. So we have to increase the depth here. Fine, we have to increase the depth. So let us increase the depth. Let us increase the depth, or what you can do, you can decide the you can say reinforcement that you are providing for the moment, and for that reinforcement you can check again. Okay, for that reinforcement you can check again. Both you can do. So if you go to moment and if I click on apply, so at the face of the column, the moment we are getting, it is around 505.1389. Here also is around 514. Okay, so suppose I'm considering 515 kilonewton meter divided by 1.2. So how much it will be? How much it will be? If I just do it, 515 divided by 1.2, so it is around 429.16 kilonewton meter per meter, right? So for this, if we provide the reinforcement, how much reinforcement will be providing? How much reinforcement will be providing? So we know AST equal to 0.5 multiplied by FCK by 500 Fy multiplied by 1 minus, I'm doing it here, root under 1 minus 4.6 multiplied by 429.16 multiplied by 10 power 6 divided by FCK BD square. So FCK is 25 multiplied by B is 1000 for per meter width, D is 740 square multiplied by B into D multiplied by 1000 into 740. Okay, so we can do this here. Let us see. Let me just yes, so if I do it here, 0.5 multiplied by 25 divided by 500, okay, multiplied by 1 minus, root under 1 minus 4.6 multiplied by 429.16 multiplied by 10 power 6. Why 10 power 6? I converted this kilonewton meter to Newton mm. Okay, so divided by 25 multiplied by 1000 multiplied by 740 square bracket close 1000 multiplied by 740. Okay, so if I just press apply, so it is 1385.77 mm square. Okay, for per meter width you are providing. Okay, 1385.77. so this is my AST that you have got. So what is the percentage of AST that we are getting? So it will be AST by BD, 1385.77 divided by BD, 1000 multiplied by 740 into 100. So it is around 0.187% that we are providing. 0.187% instead of 0.17%. So let us see. If you see here, 0.187%, even if you are providing, then also the shear stress, it will be between 0.36 only, but our stress we are getting 0.5 something. Okay, so that means we need to provide reinforcement more than 0.5%. so it is not okay. So in that case we will be increasing the depth of the foundation. So now to find the depth, doing this iteration again and again, it will take a lot of time, right? So what is the best process to do this? So we know that the VU is 375 kilonewton per meter width, right? And we know that for the minimum reinforcement of 0.17%, okay, 0.17%, the 𝗉𝐶 that we are getting, design shear strength, it is nothing but 0.304 Newton per mm square. Okay, so we know what is the VC. The shear capacity of the concrete section is nothing but 𝗉𝐶 into B into D. And if we write it here like this, 0.304 multiplied by 1000 for per meter width multiplied by D, and if we place this 375 here, okay, so 375 power multiplied by 10 power 10 cube. Why 10 cube? Because we have converted this to Newton. Okay, I've converted this to Newton. If I convert this to Newton, and these are also in Newton per mm square and Newton, mm. So in that case, you can find the D. So what will the D? D equal to 375 multiplied by you can say 10 cube divided by 0.304 multiplied by 1000. So what will be the D required? What will be the D required? So if you just go here, you can see 375 multiplied by 10 cube divided by 0.304 multiplied by 1000. Okay, so we are getting 1233.55. We are getting 1233.55. Okay, 1233.55 mm is the required effective depth. So what is the overall depth then? So 50 mm cover, then if you consider for 16 mm dia bar, so maybe again 8 mm, so you can consider 1300. So the total depth you can consider as 1300 mm. So that the load is so high that you need to have 1300 mm of concrete depth if you are not providing shear reinforcement. So as we have decided not to provide shear reinforcement, so we have to provide this depth. So what I will do, I will jump into my define slab properties. I will modify the thickness here. I'll modify it to 1300. Okay, 1300. I'll change this to 1300. I'll click on OK. I'll click on OK, and I will run the analysis and design now. Sorry, before running the analysis, let me just unlock this. One more thing we need to do, that as we have changed the thickness, so the overburden load or the soil load that we have provided here, it will also reduce, because earlier it was, see, the founding level we have considered as 1.5 meter, and now the depth of our footing itself is 1.3 meter. Okay, so only this much will be soil for us, which is 0.2 meter. Okay, this is my soil. Okay, so what we can do, we'll go to the assign. Sorry, let me just go to assign. Let me select this member, assign load data, surface loads, and I will replace this load of 13 kilonewton per meter square. It will be now 0.2 is the depth of your soil area, and multiplied by 18 kilonewton per meter cube. So 18 enter. So 3.6 kilonewton per meter cube square area load we have applied. Now to remove the load from this column location, I'll select this column location. I'll go to assign load data, surface loads, and I'll make it minus. I'll replace it. Okay, now you can see here it is 0, and the other area it is 3.6 kilonewton per meter square. Now we'll run the analysis and design, and I will see, first of all, as we have increased the depth, you have to see the pressure. So I will go to my you can say, so show reactions. I'll go to soil pressure and I will change the load to 0.1 dead load, 0.1 live load, and my earth pressure, you can say load of your mesh file. So I'll apply. You can see here also the pressure that we are getting, negative pressure of 291.05 kilonewton per meter square, which is less than my allowable gross SBC of 327 kilonewton per meter square, right? So in that case it is okay under pressure. Now if you see the deform shape, I'll go to the same load combination and click on apply. You can see the maximum deformation that we are getting, that means the displacement or settlement we are getting, it is minus 24.25. so it is also less than your allowable limit of 25 mm for isolated footings, right? So now we'll jump into the design part. So I'll just click on this strip forces. I will remove all these things, okay? And rather seeing the shear now, first of all I'll see the moment. I'll change the design design combination. I'll click on apply, and if you see the face of the column in this direction, okay, the moment we are getting 515.1695, and for this vertical direction we are getting 508, and here also 509 something. Okay, so you can say that it is around 515 to 510 to 515. So both direction, if you consider, as the values are same, so I am considering in both direction I have mu of 515, let me see, 515.16. so let me write it, 515.17 kilonewton meter per meter, and it will be divided by 1.2 because the strip width is 1.2, right? It is 1.2. so to get the moment for per meter width, so it will be divided by 1.2, which is equal to, so if I just do the calculation here, so 515.17 divided by 1.2, so it is around 429.30. so 429.30 kilonewton meter per meter width. Fine. So for this, if you find the AST, what is the AST that we'll be calculating? So to find the AST, we need the effective depth. We have considered the overall depth of 1300 mm. So the effective depth will be 1300 minus 50 mm cover, and if you consider 16 mm diameter, so half of that 8 suppose, so it will be around 1242, which we can consider as suppose 1240 mm. So this is the effective depth we are considering. Okay, so the AST that we can calculate, it is 0.5 multiplied by FCK by FY multiplied by 1 minus root under 1 minus 4.6 into 429.30 multiplied by 10 power 6 divided by FCK into B is my 1 meter per meter width, so 1000 multiplied by D is 1240 square, okay, divided by 1000 multiplied by 1240. We are getting a value of 806.78 mm square. So this is the AST required for the moment that we are getting. Now we need to also check what is the AST minimum required. So the AST minimum is nothing but 0.85 by Fy, so it is that 0.17% of 1000 multiplied by 1240, okay, of this effective area. So how much we are getting? So it will be 0.85 divided by 500 multiplied by 1000 multiplied by 1240, so it is 2108. So it is 2108 mm square. It is the minimum reinforcement required. Okay, so now as we have seen, what you understood, why I have calculated the moment first before calculating the shear, because here if you see the AST required for the analysis moment is less than the minimum AST required. Okay, so that means the percentage of reinforcement we are providing is the minimum criteria, which is 0.17%, as we have calculated earlier also. So for this 0.17% tau c, we have got 0.304, which we have used earlier also, Newton per mm square. So there is no change in the tau c. That is what I wanted to you can say show you, that the AST that I am going to provide now, for this we are not getting any higher value of tau c. Okay, so as the tau c is 0.304 Newton per mm square, so what will be the VC? So as usual, the VC will be tau c into B into D. So now the D has changed, so 0.304 multiplied by, pardon me, let me just write it somewhere else. Let me write it here. VC equal to tau c into B into D. So it is 0.304 multiplied by 1000 multiplied by 1240. Okay, so what is the VC? VC is nothing but the shear capacity of the concrete. Okay, so it will be 0.304 multiplied by 1000 multiplied by 1240. So we are getting 376.96 kilonewton as our shear capacity. Okay, for per meter width. Okay, so this is my shear capacity. Now what is the shear force we are getting? Now the shear force, where we'll be calculating? Earlier the D was 740. Now as the effective depth increased, so it is 12.1240, right? 1.24 meter from the face of the support. So here at the face of the support, we know the you can say coordinate is 0.225. So now at what equation we will be calculating? So the location will be so let me calculate 0.225 plus 1.24, so it will be around 0.465. so if you see here, from here 0.465, just check the x coordinate in this area. Okay, check the x coordinate here. Fine, as we are checking in the along the x direction, so 1.465, so it will be around 1.46. yes, here or 1.47, like somewhere here. So value is 1.465. let me see. Oh, okay, I am checking the moment. Let me change it to shear actually. Sorry. Yeah. So now the shear we are getting at 1.465 is around like this. So it is 136.97. Suppose 137. Let us check in the other direction also. 0.165. Sorry, 1. What was the answer actually? 0.225. 1.465. Yeah. So at 1.465, 46. Yeah, somewhere here it is also 137. In this direction also you can see this is 0.225 y. It will be 1.465 in y direction. Now you check this. Okay, now you check y as we are checking in the y direction. So 1.465 suppose 1.46 is same 137, and here also 137. So now we are getting VU equal to 137 by 1.2 kilonewton per meter width. Okay, so it will be how much? 1.2. Why? Because it is the strip width. Okay, so we need to divide the strip width to get the per meter force per meter width. So 137 divided by 1.2 equal to 114.114.16 kilonewton per meter width. And what is the shear capacity that we have got? The shear capacity that we have got is 376.96. Okay, so with the increase of depth, you can say here the shear has decreased right? The shear has decreased, so we are getting a very minimum value of shear here. So our shear capacity is much higher than the shear demand, so we can provide 1300 mm. So this is it. This is how we find the you can say depth of the foundation based on the one-way shear or two-way shear, whichever is, you can say, critical. And now what will be the then reinforcement provided in this case? What will be the reinforcement provided in this case? The reinforcement provided, it will be 2108 mm square. So the reinforcement, how will be providing? 2108 mm square. Fine. Now suppose we will be providing 20 mm dia bar, so divided by 314 mm square. So how much we are getting? Number of bars. So 2108 divided by 314. So it is around 6.7. So you can say 7 number of bars we require in 1 meter width per meter. Okay. So now if we calculate 1000 mm divided by 7, what will be the spacing required? So 1000 divided by 7, so it is around 142.85 mm, and we never provide this kind of spacing. So we always provide spacing in terms of, or you can say in the multiples of 25. So it will be, I can consider the less than this value, which is 125. Okay, so we'll be providing T20 at the rate 125 mm center to center both ways. Okay, so I hope this is clear how we provide or actually how we decide the reinforcement, how we decide the depth. So if you have any doubt regarding this, you can always ask me in the comment. I will try to solve your doubt. Okay, so thank you. I will see you in the next lecture.